Today in this video lecture, we will see numerical 4 on design of shaft. Numerical is a steel shaft of 950 mm diameter is required to transmit 220 kW power at 225 rpm revolution per minute and maximum torque is 40% greater than the mean torque. Find the maximum allowable shear stress in the shaft. So in this numerical, they have given us data. This is shaft and diameter of that shaft is 950 mm and power is 220 kW and number of revolutions per minute is 225, and they also tells in this numerical maximum torque T max is equal to 40% greater than mean torque. That means T max is equal to 1.4 into T mean, and we have to find maximum allowable shear stress. So from this data we have to find this maximum allowable shear stress. We will see in this numerical steps for solving these numericals. So first write given data. Diameter denoted as small d, 950 mm. Power is 220 kilowatt. That means 220 into 10 raised to 3 watt. Number of revolutions 225 revolution per minute, and maximum torque is 1.4 into mean torque. Maximum torque is 40% greater than mean torque. Here mean. And from this data, diameter, power, number of revolutions, 1.4 into T mean is T max. We have to find maximum allowable shear stress, tau max. So methodology for solving this numerical is, first we have to use power formula. P is equal to 2 pi n t upon 60, and from this power formula we find mean torque, and from this mean torque we find this T max, and after we use polar moment of inertia formula, and by using torsional formula we will find this T max. So see step by step this numerical. First step, power formula. P is equal to 2 pi n t, and this t is T mean upon 60. P is 220 into 10 raised to 3. N is 225. And from this equation we will find this T mean. So T mean as it is, and divided by 60. So T mean we get 220 into 10 raised to 3 multiply by 60 and divided by 2 into pi into 225. So T mean is 9337.09, and unit is Newton meter. And from this T mean we will find T max, because we know relation between T max and T mean. T max is equal to 1.4 into T mean. So this T mean is 9337.09. So 1.4 into 9337.09 is 13.072 13.072 into 10 raised to 3 Newton meter. And this Tmax in Newton mm is 13.072 into 10 raised to 6 Newton mm. So now next step is polar moment of inertia. Polar moment of inertia for that solid shaft is pi by 32 into d raised to 4. And d is 950 mm. So this polar moment of inertia pi into 940 raised to 4 divided by 32 is 7.665 into 10 raised to 10 mm raised to 4. Moment of inertia unit is mm raised to 4. And this value is 7.996. So this polar moment of inertia is 7.996 into 10 raised to 6 mm raised to 4. And third step is using torsion formula. We will find tau max, maximum shear stress, maximum allowable shear stress, and torsion formula is T by J, twisting torsion upon polar moment of inertia, is equal to G theta upon L. G is shear modulus, theta is angle of twist, L is length of shaft, and tau is shear stress upon R is radius of that shaft. And in this numerical, we don't know shear modulus value, angle of twist value, so avoid this portion. And our objective is to find this tau. So this tau we will find by using relation between both of these. So use T by J is equal to tau by R equation, and this tau is tau max. So tau max is equal to T by J into R, and T here is T max 13.072 into 10 raised to 3. 3 not 10 raised to 6. Use Newton mm value. And radius is 950 divided by 2. 475 and J is this 7.996 into 10 raised to 10. So this tau max is 13.072 into 10 raised to 6 into 475 divided by 7.996 into 10 raised to 10 is this tau max is 0.07765 Newton per mm square. Stress unit Newton per mm square. So see this numerical, this is steel shaft, and in numerical given data is diameter, power, number of revolutions, and only relation between T main and T max. And by using these four given data, we will find this. We had find this tau max, and see we had used this torsion formula T by J is equal to G theta by L is equal to tau by R, and this polar moment of inertia J is equal to pi by 32 into d raised to 4. This polar moment of inertia initially we calculated for this torsion formula, this polar moment of inertia required in torsion formula, and by using this power formula we had find this torque. So this is solving methodology of this numericals. And both of these data we had required, both this T max and J require in this torsion formula, this T max 13.072 and J is, that's why we initially calculated this torsion, maximum torsion, or you may call this torque, maximum torque, using this power formula, and polar moment of inertia by using this formula. So three formulas we had used in this numerical. One is torsion formula, one is polar moment of inertia formula, and one is power formula. And by using power formula we calculated maximum torque, and by using torsion formula we calculated maximum allowable shear stress. And shear stress unit is Newton per mm square, polar moment of inertia unit is mm raised to 4, and torque unit is Newton mm or Newton meter. And see, I had used Newton mm value in this torsion formula. This maximum torque value is Newton mm. I choose to put this in torsion formula because I need this maximum shear stress in Newton per mm square. So put Newton mm values in this formula. J is in mm raised to 4 and maximum torque is in Newton mm, and R is also in mm. So that's why this maximum torque is Newton per mm square. And when you solve this T mean by using this power formula, so this T mean unit is Newton meter, and by using this power formula you get this T mean Newton meter. And in numerical they have given us relation T max between T max and T mean. So by using this relation we had find this T max, maximum torque. So thank you very much.